Hi, in this video we're going to cover the download of the ENCY project for the Batman bust that we're going to be machining, and we're also going to cover the initial setup and the first toolpath operation for it. So to access this, we go to the ENCY project library, which is under the open icon. We hover our mouse over it and then click on project library. This is a free online resource available to all ENCY users, and it contains nearly 400 projects which are covering a variety of different machine types and machining operations. However, since there's such a significant number here, we're going to close the field down slightly by clicking on machine type and choosing robot 6 axes, and then scrolling down to the project that we want, which is this one. And it lists here how it comes with a KR90 milling cell configuration as well. All of these projects will have the cell definitions or machine definitions set up for them already. So we can see here a nice preview picture of the cell and a preview picture of what the finished part is expected to look like. So we click on Open Project and it will prepare and download the file for us. Now that that's downloaded, we can close the window and we should see the project prepared for us here. So as we can see, we've got our robot definition in place. There's already 3 toolpath operations set up because the whole point of these projects is for you to be able to download them, see how they're done, work through them yourself, and go through all the operation setup work that's involved as well. So we're going to delete these operations that are currently defined because obviously we want to work through them ourselves. So the first thing that we need to define now is the robot tool orientation, because at the moment it is facing downwards. Now the robot tool orientation is defined according to the robot's own frame of reference to where it is in the world. It doesn't pertain specifically to the workpiece that it's aiming at. So to set this, we can either double click on click to pick, or we can single click and then click on the ellipsis next to it. And we've got 3 options for defining this. We can either use one of these cardinal directions here, or we can use view vector, which determines the vector based on the current viewport angle compared to the robot's position in space, or we can define the vector manually. So I'm going to define the vector manually. I want +1 in X and 0 in Y and Z. So to do this, I'm going to enter 1 and then set Z to 0. And you can see how it's automatically set the cardinal direction to right. So we click on OK now to define that and lock that in. The next thing we want to do before we start defining a toolpath is we want to set the workpiece, which is this translucent orange cube surrounding the Batman bust. There's already one defined, but we want to set ours ourselves. So we click on this and we delete it. Now, to define a new one, we want to click on Primitive, and by default that will set itself to a box around the part, since that's generally the most simplistic and common form of stock material. We want to set this to have a 5mm offset just to make sure that, there's a little bit of material to work with. So I'm going to click here and press 5, and we can see how all of these boxes are now auto-populated with the number 5. Now we don't want 5 in -Z because that will cause the machine to try and machine the underside of our statue bust, which we don't want. So I'm going to turn off same stock, which is the setting that forced all of these to correspond the same, and then set this to 0 and then click on add. And if you watch closely, you'll see this box expand slightly as a result. There we go. Now that's the core setup done. So the next thing that we do now is we want to define an operation. So again, 2 ways of doing this. We can either click on Add Operation here, which will give us a pop-up box with a preview of what the operation is going to look like, or we click on the drop-down menu option here. Once you know what the various operations look like, the drop-down menu is generally a quicker way of doing it because there's no extraneous text boxes left to close. So I'm going to click on this, go to 3D Entry, and then roughing waterline. Now, what we can do is we can try generating a toolpath straight away. It won't be a perfect toolpath because we've not given it any definitions and settings beyond this is the way that you're facing, this is the object that you're cutting. But it'll give us something, so it's worth a look. So we click on Generate Now, and you'll see it generates a toolpath fairly quickly and cleanly. It does, however, complain about some segments of the toolpath will not output due to limits of machine tool, which basically means if we click on Front on the navigation cube here, we can see that compared to the length of the tool path itself goes a lot deeper and it goes outside of the available reach for the cutting tool. This is fine, it's not a problem. We can easily define a base layer for it to stop at. So to do this, we click on Strategy, and under Machining Levels, it lists the top level, which is where it starts machining, and the bottom level, which is where it intends to finish. Now obviously this tool can't reach the far end of the block, so what we're going to do is we can either set a numerical value here, or we can drag this plane, and it is a plane, see, to a neater center point that works better for us. So I think around -5 here looks good. Now we can see that we've still got the step down layers defined by these grey lines here, and we have got 1, 2, 3, 4 and a bit, which is not really ideal. It's not the most elegant solution. So we can set that to be proportionally determined instead of being to a fixed depth, because at the moment the depth step is set by the size of the tool and it's set to 30mm absolute. So what we can do here is we can click on this, and over on the right there's a little drop down tab here, and we can set it to count. So instead of the 4 and a bit that we had, we can set it to 4, and that means that each depth step will be somewhere in the region of 31 or 32mm. So we do that, and we can see now how it's neatly defined these 4 lines right down to the point that we set with the green plane. So I'm going to click Generate Now, and we'll be able to see that we've got 4 nice neat toolpaths, all of the same depth, not constrained by the tool size as such, although well within the tool's reach. The next thing that I'd like to change is these steps. They're a bit aggressive, and especially this one in particular is likely to cause us problems. If the tool accidentally clips it or something, it'll take off the entire tip of the nose. So we've got a nice interpolation tool built into ENCY called Step Up, which allows us to define a set of sublayers, which are contour passes, which will smooth out that step into something closer to a curve. So to define Step Up, we click on the Step Up entry, click on the down arrow, and then click Constant. Now, if we regenerate the toolpath, we'll see the difference. Notice how with each setting that we're defining, the toolpath generation takes very slightly longer. Obviously, the more constraints that we set, the more calculation that the software's got to do for how to get the robot to achieve the end result. Now we can see we've got these smaller subpaths going on between each of the primary step-down paths. And if we turn off toolpath visibility, we can see how we've got some much smoother interpolation between the final shape and the roughing pass. This is good so far. The next thing that I've noticed is just how close it is to the actual final model. Because this is a roughing pass, we want to give it a little bit of extra meat to be able to work with, so the finishing pass has got something to do and there's no roughing tool marks in the final piece. So the way to do this is we go to the Parameters tab, and in axial and radial stock we want to set that to a higher value than 0. So I'm going to set it to 5 in both of them, because I'm assuming that this is to be machined out of a soft material like foam. We can give it a nice amount of access, and it makes it very clear for the sake of example. So if we regenerate the toolpath once more, we'll see that there'll be an offset now. Give it a second to generate. There we go. So we've now got that nice offset between the stepped path and the final workpiece. So the next thing that we need to do is we want to simulate this, because obviously this is a very nice background simulation that gives us a clear indication as to what we're expecting the final piece to look like. But it doesn't calculate every aspect of the toolpathing, and there may be errors that we haven't caught yet. So the way to do this is we go into the simulation environment and we choose a viewpoint that we're happy with to see what's going on with the machine. And now I'm going to slow down the machine speed slightly. That's what this scroll bar here does. It slows down the movement speed of the simulation. And there's something that I want you to take note of before I click on run, and that's this node status here. We can see at the moment that these are white. This means that this is an unproven toolpath. Once it's been run and the results are known good, they'll turn green. Once it's been run and it runs into an error, that will turn red. Okay, so it's a very, very easy top-level view to be able to determine whether or not all of your toolpathing is correct and working. So now I'm going to click on run, and we should see the robot start to move. Now, generally, as a matter of good practice, when dealing with the initial approach and return, I tend to run it very, very slowly because it means we can see if there's going to be any crashes that we're not expecting. Once the machine is actually engaged with the workpiece, we can speed it up a bit. We'll still be able to catch errors as they happen, because anywhere that causes a problem will usually flash red. Plus, at the end of the toolpath, we will see highlighted errors in the overall toolpath definition, which we'll possibly see in a minute. So I'm going to speed this up a little bit. But before I do, we're going to see these tiny little interpolated toolpaths that I was talking about. Notice how these are just individual contours as opposed to a whole new step-down layer. It's a much more time-efficient way of achieving the result that we're after. And we've just had our first machine collision. So it's telling us that the motor hit the turntable, which is obviously something that we cannot have happen in real life. One of the great strengths of ENCY is that it simulates the whole machine kinematic set as opposed to just the toolpath surrounding the cutting bit and the workpiece. So it allows us to catch errors like this with much more complicated machining setups like this multi-axis robot system. So we now know that there's an error and there's a problem that we need to resolve. So for the moment, I'm going to let it finish, and then we're going to go back into the machining workspace and see where the issue has come into play. There we go, again, flashes bright red when that happens. It's a nice easy visual cue to see that something's amiss. And as I say, this is showing what's going on in each of the toolpath definitions. So here we can see at level 56.635, which is very descriptively named, there is an issue where, if we hover over it, we've got the collision of machine nodes. So as I say, the actual spindle head hit the turntable. This is easily resolved though. So if we turn on toolpath visibility again, we should be able to see that. And right here, we've got these purple lines. These purple lines indicate links and leads between toolpaths. Links and leads are transition moves made between cutting paths. So to resolve this, we go to the links and leads menu, and we can see that the go up if farther option is not checked. Now what this means is if there is a link between cutting paths that exceeds the length defined in the go up if farther setting, then what it will do is, instead of following that previous link, it will pull the tool away, move up to the safe plane, and then reapproach for the cutting path. So if I turn this on now, we can see that 500 millimeters is the setting, so half a meter. It's not a small distance in this regard, but it should be sufficient. So if I now regenerate the toolpath operation, we'll see that these links down here have disappeared. This means that each time it was going to pass down here instead, the robot returns to the safe plane and then moves to where it needs to go and then comes back in instead. This is much, much safer generally. Now, there are a couple of other definitions that need setting as well. The first is I would like to set the checking of the tool and spindle holder. Okay, so the easiest way to do this is if we go to parameters, and we then look at check holder. This will make a point of allowing us to define safe zones around the tool and holder and the spindle. So if I click on check spindle now, you'll see that this red highlighting has come up. This now tells ENCY that the robot is not to move in a manner that causes this red exclusion zone to intersect with the workpiece at any point. Okay. We can also adjust for things like tool holders, such as collet nuts or anything, by changing the tool angular clearance. So if I were to increase this by, say, 30 degrees, you can see that cone is expanding around the tool now. This is very useful, especially in the case of collets, which aren't always the same shape. Some of the nuts are very, very low profile, some are much bigger in profile, and this gives you a little bit of extra exclusion area to make sure that what you're doing is absolutely safe, because the last thing we want to achieve is breaking a tool unnecessarily. So we're going to zoom back out now, and we're going to click on Generate Toolpath again. And we now have a nicely defined toolpath with no long links going down there, with hopefully no intersections with anything. However, there is one more minor problem that I would like to address, and that is the amount of roll-off down at the bottom here, where the toolpathing effectively goes underneath the bust almost. Now, we don't want it to do that, because as soon as it starts going underneath the bust, it means that it can affect this plinth that the bust is actually stood on. And we can't have that, because that's holding the bust in place on the turntable. So what we can do to combat this is, if we go into the relevant view, which in this case is back, we can see that there's this nicely defined green polygon here. Now, this is the perfect candidate for an exclusion zone. And if you can't select this at the moment, turn on Select Curves in the selection menu here. To make use of this as an exclusion zone, we go over to the Job Assignment tab. We highlight this, and something that's worth noting for future, before I get too far into this, if we scroll out, we can see there's a set of drawing commands available to us here to be able to define our own exclusion zones. Since there's one already here, I'm going to make use of this. So I zoom back in, I click on this polygon to select it, and I then click on Restrict Zone. And that defines a nice clear boundary area that the robot can't go into. So we now generate the toolpath one more time, and we should see a nice neat cutoff around here where the tool descends no further. There we go. So we now have a very nicely defined roughing path, I think. So I'm going to go into the Simulation tab now. I'm going to reset the simulation workpiece, so that now goes back to being a basic grey block that's unmachined. Pan around a little bit so we can see it a bit more closely. And then I'm going to click on Run. Now, I'm not too worried about the speed of the approach in this instance, because I know that the approach is fine. I'm going to leave it running at this speed so we can see if there are any issues that we need to catch. I believe that we've forestalled all of the issues that were previously coming up. We've got a nice clean cut down at the bottom, so we haven't lost anything from there. We've got the nice interpolation that we were talking about before as well. So we've got a very, very smooth, very nicely roughed out bust so far. I'm going to speed this up a little bit, because otherwise we're going to be here all day. And you'll notice that we've not had any errors manifest so far about machine intersections or tool intersections or anything like that, because of all of the exclusion data that we've given it, especially the check spindle data as well. And there we have it. We have the first pass of our roughing, and you can see that the node is now a nice green status, which tells us that it's good to use. So in the next video, we're going to cover the second roughing process, and then in the final video, we'll cover the full finishing process as well. See you then.